What's up? Welcome to Earth Science, everybody. How we doing? Let's tackle these two pages today in this lesson, page 4 and page 5 of the note packet, which will, again, it'll be linked in the survival guide. That's how you got here, and all that stuff should already be done on your assignments. Let's talk about tectonics and go way back. Like, why does all of this stuff happen? And we'd have to go all the way back to Unit 1, which is, for some reason, September this year with all the COVID stuff feels even longer ago than most Septembers do. But if we can go way back, maybe we remember that our solar system formed out of this interstellar cloud of gas and dust. I'll pause for a sec. Anybody remember the name of that interstellar cloud of gas and dust? It's called a nebula. It's like gas and dust in space, easier than interstellar. And what would have happened out of there is, as gravity, basically you had to get to like this critical density, and as gravity took over, started pulling things closer and closer and closer to the center of mass of this whole entire big mess, because as things get closer, they feel more gravity with each other, which means they came together, which makes them more massive, which also means there's more gravity. Like, you get more mass, so there's more gravity, so you pull more stuff, so you get more mass, so there's more gravity, so you get more stuff, so you pull more mass, so there's more gravity. It's called positive feedback. It just keeps going and going. In the middle, there would have been this protostar, early star, with this disk. As it started to spin, you get into a little physics, you see why they start to spin and flatten out. And then eventually, kind of on a smaller scale, almost the same thing kept on happening with big chunks of debris, frozen gases, or rock that maybe we would call protoplanets. Like, proto just means like kind of early version of, like a prototype, you know, protostar. Oh, it doesn't like that. Protoplanets. No, that's worse. There we go. And eventually, we'd end up with, once we got this thing to be heavy and dense enough. Anybody remember the reaction that powers stars? There's another flashback to the first units. Once it's heavy and dense enough, fusion can power all stars, plus the sun, which is a star. And eventually, the orbits of all these planets got pretty much cleaned up, except for the asteroid belts, and formed into the 8 planets, plus the dwarf planets and the asteroid belt. Okay, great. Why are we going back and doing all this? Well, if we went and saw the very, very, very early Earth at this stage, as it was getting bigger and bigger and bigger, and then attracting more particles, and things are slamming into it, and that creating heat energy as that happens, it would have at first essentially been kind of like a big kind of uniform chunk, right? But as those impacts continued, and as this thing heated up, and as it got bigger and smushed in on itself with, friction creating some heats, we ended up getting enough heat in here that you could create some melts below the surface. So this would have not been a happy time to live on Earth. I mean, you wouldn't make it more than a couple of seconds. No atmosphere. The inside of the Earth is melted, so there's a very, very, very thin crust. Plus, there's still constant bombardments from the very messy early solar system. So if we go like way forward on that, what that allowed is that the more heavy, the more dense materials sunk down towards the middle, what we today call the inner and outer core, whereas the lighter, more buoyant things would have worked their way up towards the surface. This process, and I'm not expecting that you'll really ever see this word, is called differentiation. I don't know. If you skip that, I can't say I'm too mad at you, but doesn't want to make it bigger. Sorry. Differentiation, which just means the layers are like getting different, right? They're taking on their own characteristics because they're separating out by their characteristics. What is the driving force here? Behind all of this and behind all of this, it really ends up coming down to gravity. There we go. Nice big letters. Gravity. Okay. So what that allows us to do now is say, okay, inside of the Earth, we've got these layers, we've figured it all out, and we can also go and say, here's what the properties are inside. Now, the top of the reference table says, and this is important, inferred properties of Earth's interior. If you were with us for these notes right here, you know that even the most ambitious drilling project ever taken place, which took decades, made it 0.2% of the way down into the crust. Whereas, well, not whereas anything, that's it. We haven't directly observed any of that other stuff, the other 99.8%, right? So how do I have the audacity to say, here's what's going on? How does New York State have the guts to put this in a reference table? Speaking of which, this is a reference table, so you're going to want to get comfortable with this thing. Page 10 of your Earth Science reference tables looks like that. Now, I had this chunk in the very top of the notes when we first talked about the very outer layers, but now we're going to have to go and do a bit more. So here's what I want to see you do. This may feel juvenile. You may say, I'm not a kid. We don't need to be drawing or coloring. I'd really like you to do it. And let me tell you why. Pick a color, whatever color you want. Bring the transparency down. And what I want you to do is color start of the inner core. If you made it red, cool. If not, that's also cool. Okay? Now, the reason I'm doing this is because, and believe me, this helps people see how this thing works. If you say, like, I don't need to do this, I'm not a kid, do it. It's only going to take a couple minutes, and it's going to help you see how this whole entire graph works. Because from this, we can ask, we teachers or regents exams, can ask about the density, the pressure, the temperature, the depth, the thickness of all these layers. You got to be able to extract all that information, which sounds a little intimidating. But this will help. So if you say color this red too, so the inner core is that, and then you see this dotted line that goes down? You're going to color right down that dotted line. Not super neat. And, you guys have played with Cami enough. If you make your pen a little thicker, maybe this is easier. We do this every year. This is normally colored pencil. And again, I really recommend it. All right, so now the reason I do it is because this is going to show you that everything in red there is the data that goes with the inner core. And then pick a different color. Hope that the shading is, yeah, it is. Okay, pick a different color and do the outer core. And now again, in this case, it's going to come right over here. And then all the way down to here and back up. Then you're going to keep on doing that. It's a little weird looking if you unclick. But again, you guys have done enough of this. All right, something like that. Then do it again, then do it again. I usually say just do 4 colors. You can try to do one tiny little, I guess if you blow it way up, that last one might be a lot easier. But your call. So give me at least 4. You could do the whole top from the astenosphere right to the top if you want, or you could try to do 1/5 color right down that little narrow column. Again, like we said on the first page of these notes, this does not do a great job of talking about the near surface stuff. It's better for the deep tectonics stuff. All right. So how does it all work? Here's the premise. If you need to know the stats of something, let's say the boundary between the mantle and the core, right there, where the outer core ends and the stiffer mantle begins, or vice versa, right? That line right there. If I need to know don't draw these lines because it's gonna turn you into mess. But I'm gonna do it so that you can see. If I need to know the pressure of that line right there, what I do is I come to this line. It says pressure right there, that line. So the pressure at that line right there, I'd say is about 1.5. There's a label here too, million atmospheres. Okay. The temperature, if I need to know the temperature at that line, again, between the stiffer mantle and outer core, looks like it's about 5,000 degrees Celsius. Okay. If I need to know the depth of that, you come right down and it looks like it's a tiny bit, not quite to 3,000, so maybe 2,950, right? What if I had to do the thickness? If I had to do the thickness of this layer, I'd say, well, if I know this depth and I know this depth, I could figure it out. You could just subtract the two to figure it out. Okay, now you're going to practice a bunch of these, and it's one of those things. And again, who knows what this Regents is going to look like, or whether you'll be doing it at all. But it's one of the things that will be on the test that we're going to do for this unit, and would definitely be on the Regents should you take it. Okay, so color the other two, and start to think about how you can just interact and get those lines. Density is also listed over here. So the outer core can have a density anywhere from 9.9 to 12.2 grams per cubic centimeter. Another very valuable thing that's like hiding here, I'm going to blow it up, is this little thing right here tells us that we've got two types of crust. And that's going to be critical, probably not this week, next week, to get this difference between continental crust and oceanic crust. But here, and this question pops up all the time, and I'm telling you, people get it wrong all the time because they don't think, oh, it's just, it's information right here. People think, oh, I didn't remember that. I don't know. Continental crust tends to be granitic at a lower density. Oceanic crust tends to be basaltic at a higher density. And sometimes what they'll do, they'll be extra mean and they'll say felsic or mafic. So you would either have to know that one of these is felsic, one of these is mafic, or know that we've already done the rocks unit. And you could very easily go to the reference table, figure out which one's which. Granitic is felsic, basaltic is mafic. But that's on the tables. All right, one other thing, and we'll wrap it up. We're not going to do that. If the temperature of something is above the melting point, what phase are we in? The temperature of the water in this jug is above the melting point. So what phase is it in? If the temperature of this water were below the melting point, what phase would it be? All right. Solids and liquids hopefully are entering our minds. So we've got this quirky thing right here. And this is one of those that some people just memorize, or some people just always say, I can always go to the table and I can see. Here in this layer that I colored blue, the temperature is above the melting point. And if the temperature is above the melting point, you got yourself a liquid. Whereas here, the temperature is below the melting point. That makes it a solid. Here, the temperature is below the melting point. That's a solid. In the asthenosphere, you get a couple of weird chunks where maybe you get some sections where there's liquid. That's in fairly specific circumstances, though. But we're going to say, as a whole, the outer core is the only layer that truly behaves as a liquid. And you were saying, hey, what about I saw that volcano in Iceland going off on YouTube? That looks like liquid. That's coming from the inside of the earth. And like, yeah, that's true. When you release the pressure on magma, it turns liquidy. But since everything in the asthenosphere is under pressure, pressure does weird things to temperature. That's hard to picture. But if you put, you could put enough pressure on this water at this temperature to turn it into a solid. Pressure monkeys with melting points and freezing points. And you'll do more of that in chemistry. It might be a little bit of a leap here. And if all of that's like, what the heck is this guy talking about? Hey, outer core's a liquid. Boom, that's it. Like if you can get that, then we're happy. Okay. All right. How's that all sound? I'm going to do a separate quick video to show you what you're going to do to practice some of these things. I've got some practice questions over there, but I think I'll do that separately. You did these notes. Good job. Take a breath, take a break, and we'll go on with the practice in a moment. All right. Thanks, folks. We'll catch you soon.